Okay, we're covering section 13.7, and the objective is to use parametric equations to represent motion in a plane. That's our objective. Uh, use parametric equations to represent motion in a plane. Now, before I tell you what exactly parametric equations are, I want to explain, I want to review a little bit about what we've been covering the first half of chapter 13, because this is actually the end of chapter 13. This is section 13.7. 13.7, and there should be a dot, not a dash. 13.7. And so what I want to do is show you, that thing we've seen 100 times. This web page, cool math. It's really good circle stuff. So what we first learned just last week was to start putting degrees on the coordinate plane. So we put our degrees on the coordinate plane. That's down here. So we zero and we rotate slowly. We open the door. It's quarter turn open. That's 90 degrees. And a half rotation sends us to the other side of the x-axis, 180. And we go down here. It's 270. And over here it's 360. And we can keep going. 450, 540, 630, 720. Or we could go negative 90, negative 180, negative 270, and so on. Those are 90 and 450 are examples of coterminal angles because they're 360 apart. But rotations on the coordinate plane, we could map it out like this. But what these angles are measuring is angles. How many turns have been made? Those aren't points, right? Those aren't points. They're angles. You want to see it visually in another way. You can see it right here. The angle is down at the bottom of the screen. You can see getting bigger and bigger and bigger. See, it's almost a full pi. That's 340, 354 degrees. It's almost a full circle, but not quite. And now it's not showing us the 365 or whatever. They're starting over. 0 to 360, see the whole thing. But the points out here, well, what are those? What are those? Well, it turns out the points match up with sine and cosine. And these are the points. These are some of the points. Now, hopefully you know this already, but that would match up with a 30-degree angle. This being a 30-degree angle touches those points if the radius is 1. 45 degrees, 60 degrees, 90 degrees, 120, 135, 150, 180, 210, 225, 240, 270, 300, 315, 330, 360. I didn't have to memorize them. I just memorized 30, 45, 60 and added that. So this is 90 plus 30, 90 plus 45, 90 plus 60. 180 plus 30, 180 plus 45, 180 plus 60. There are innumerable points here. We only map these out because we love our special right triangles so much because they helped us derive these values for sine and cosine, and we've memorized them. So on the unit circle, these are points on the unit circle. The angle itself, the 30, the 45, the 60, it's not on the graph. It's a third variable that's not on the graph. This is an XY graph. 30 is not mapped here. 45 is not mapped here. 360 is not mapped here. It's a third variable. So what to do with that third variable? Well, that's what parametric equations are all about. Parametric equations, we get, the way they're used, your third variable, instead of being an angle, your third variable is time. And it's like, okay, let's say an ant is crawling across a picnic table. This is the edge of the picnic table. We can map the picnic table. We can call this 0, 0. And the ant is going across like this. Well, then there will be one equation relating x to t and one equation relating y to t. Like maybe, and the way that'll end up looking is there's t, there's x, there's y, and after 0 seconds it's at 0, comma 0, but after 1 second it's at 2 comma 1. After 2 seconds, it's at 4 comma 2, and so on. And with this information, our graph is these points. We don't, the t doesn't show up on the graph. But we could make an equation relating x to t. And maybe you can see it. Yeah, x is always double t. So x equals 2t. I should write that some other place where it's less scribbly. And what's the relationship between y and t? Hopefully you see it. If you look at t, look at y, they're the same. How do we say same in math? Equals. So these would be our two parametric equations, and they combine to make this graph. And so that's what this chapter sort of gives us. And then we can, given two equations like this, we can get an equation relating x and y. Like, let's say, oh, you're given this, now eliminate the parameter. X equals 2t, y equals t. So the trick for this is just substitute. So substitute your value for t into the equation. Anyway, like for example, in this it's easy. We want to replace x and y. We don't want t anymore. Well, what is t? Well, it's y. So we just substitute in, and now we have our equation relating x and y. That's called eliminating the parameter. Eliminating dot the parameter. Okay, so you start out with two parametric equations, you use substitution, and now you have an xy equation. You eliminated the parameter. Graphing, using this to graph is like another way of eliminating the parameter. If you have this table of x's and y's going that you could get from here, and you can plot it, and this graph is an xy graph. It's not, there's no t on the graph. Okay, so that's eliminating the parameter. We're going to have two important parametric equations that we're going to use to find the position of an object, because like we said, our objective was to use this to represent motion in a plane. Well, when we anytime we have a linear situation like this, it turns out that whenever an object is moving with constant speed along a straight line, and its angle of elevation off the x-axis is theta, like this. There's theta. But theta is going to be a given, so it's not a variable. T is still our variable. Yep. So then we might have x, or we have two parametric equations describing the movement, the position of x and y relative to t. So x relative to t is x equals parentheses velocity, the initial velocity, times cosine. They're just initial, no, it's constant velocity. There's no initial or nothing. It's just the velocity. Cosine theta. So velocity times cosine theta. And here's the initial part, plus wherever x started out. Initial x. So the new x is is velocity times cosine theta plus initial x, where x started out, and y equals the same thing except one variation. Maybe you can guess it. Here it comes, sine theta plus initial y. So those are our equations, and x0, y0 is where the object is when t equals 0. And then as you start moving, velocity moves the object. And the sign of, maybe it makes sense, as theta, I guess as the angle gets bigger and bigger, then we start moving up more, right? But if the angle is smaller, we can move that way more. I actually, ignore that last thing I just said. Ignore that. But use these equations. So, for example, at a softball throwing contest, you throw a softball with the speed of 60 feet per second. This is number 10 on page 816. And you throw it at an angle of 50 degrees from, I guess that's your angle of elevation, so it's throwing 50 degrees up in the air. And your initial height is 5.5 feet. So what are the parametric equations that show what the xy of the ball is? So the way I'm going to imagine this is, imagine you're standing at 0, 0. But then the ball's initial position is actually at 0, 5.5, because that's where that's your initial height. And then if that's a straight horizontal, it will be like this. You're throwing it at 50 degrees. Oh, but wait. Problem, the equations that I just gave you are different for this situation. This is for describing a straight linear path. But in this case, we're not going to, is our ball going to go on a straight linear path? Are you going to throw that ball that's just going to go straight like this forever? No. Why not? Oh yeah, because we don't live in space. We live on a planet with a little something called gravity. So our x equation doesn't change, but our y equation does. Gravity pulls on our on this thing. So we still have, these terms are still part of it, but when we're dealing with a projectile going into space, or when we're throwing a projectile, we have this other gravitational constant that goes in front of everything. G is that gravitational constant, and G is (32 feet per second squared, or 9.8 meters per second squared. This problem is in feet, so we'll just use 32 feet per second squared. It's that plus v sine theta plus y theta, y initial. So this, right, parametric equations. Okay, the x one is the same. It's going to be velocity 60 times cosine 50, because 50 is my angle, theta, plus initial x is 0, so that's it for my x. My y is going to be negative 1/2 g t squared. G is, just verifying we're going in feet here, right? Yep. So 1/2 32 times t squared. Wait, hold up. Yep. There's t squared. Where was t going to be in this? Oh yeah, I forgot. Okay, that's a part of these equations. T. Dang it. Bad teacher. All right. Cosine 50 t. It's a linear term there. All right, so down at the bottom we got negative 16 t squared plus 60 sine 50t.
that's a degree symbol.